Immutability is a major feature of blockchain technology, which you can loosely define as the inability to replace data that has already been validated by the network and written to the blockchain. In the case of Bitcoin, transaction data is hashed using the SHA-256 algorithm. Every hash within a block is combined or concatenated into a single root hash. The hash of the previous block header, which contains the previous block's root hash as a kind of metadata, is added to the next block to form an unbreakable block chain. By unbreakable, we simply mean that any change to a block made by a malicious actor will be detected by the network because that root hash, and therefore that metadata, will be altered. In a proof-of-work blockchain like Bitcoin, an attacker would need to have the majority of the hashing power in order to force the network to accept an altered block. In a proof-of-stake network, an attacker would need to own a majority of these staked coins, which is possible, but also more costly for an attacker, especially on a larger network. Generally, it's easier and cheaper for a bad actor to compromise data on a smaller blockchain because they need either less hashing power or a smaller stake. Anchoring is a process of inserting data, usually from a smaller blockchain or also an off-chain database, into another blockchain, usually a much larger and more secure blockchain like Bitcoin or Ethereum, to give you an immutable and verifiable receipt. Anchoring works by taking a bunch of transactions, hashing those transactions, deriving a single root hash from those individual hashes, and then putting that root hash into another blockchain. If the party that created the anchor maintains a record of the data that created those individual transaction hashes, then anybody with access to that data can derive the anchor off-chain and verify that it matches the anchor on-chain because the hashing algorithm is deterministic. This means that a given input value will always generate the same hash value. Factom pioneered anchoring in 2014 when it developed the technology to bundle transactions into what are called a directory block, then insert that directory block hash into a Bitcoin or Ethereum transaction. To anchor into Bitcoin, for example, Factom simply added its 32-byte anchor to Bitcoin's 80-byte OP return field. Factom anchored into Ethereum by sending its directory block hash to a particular smart contract address. Accumulate will periodically anchor into Bitcoin and Ethereum, although it's possible to anchor into any blockchain for that matter, or any non-blockchain based database. Because we're anchoring into other blockchains, data from Tezos, for example, can be validated through an Ethereum smart contract using Accumulate as a bridge. That's one way we enable interoperability between different blockchains. We can also use anchoring to prove private data from a single source. Data oracles primarily deal with public data that is broadcasted online. Examples include a weather sensor that provides local temperature, or an exchange that provides live stock prices. Data oracles like Chainlink may have networks of nodes that collect this public information and feed it back to the network that may either take the mean or mode of that data. However, most private asset data, which is a $500 trillion market, is single source, which makes it very hard to verify the accuracy and the ownership of that data. For example, the rent rolls for a major property manager could be altered by a man-in-the-middle attack and reported as accurate data to a data oracle. Accumulate's anchors on a host blockchain like Ethereum allows smart contracts to cryptographically verify the data proofs against their native chains by tracing them back to Accumulate. Accumulate is organized around URL-based identities that we call Accumulate Digital Identifiers, or ADIs. You can read more about ADIs in the previous videos or in a white paper. The important point here is that an ADI is basically an ever-growing Merkle tree that has branches comprised of sub-identities that we call sub-ADIs, accounts within those ADIs and sub-ADIs like data accounts and token accounts, authorities that we call keybooks, and signers that we call key pages. You can also read more about Accumulate's keybooks and key pages in previous videos or in a white paper. Every ADI, account, keybook, and key page is an independent chain that has state. An ADI has a main state that's composed of the URL of that ADI and the URL of that ADI's keybook authorities, and also a chain state that's composed of the root hash of every chain within that ADI. The main state plus the chain state is what we call the identity state. If an account manager has an ADI on Accumulate, an anchor of their identity state will be sent to Bitcoin or Ethereum along with an anchor of their transaction data, allowing an oracle to query Accumulate to verify that a transaction or a change to an asset was made by a particular account owner at a particular point in time. In this way, Accumulate can verify single-source private data that accounts for the majority of financial data in traditional markets and usher in the fourth financial revolution in blockchain after Bitcoin allowed peer-to-peer transactions, after Ethereum put business logic on the blockchain, and after data oracles gave blockchain access to off-chain data.